So today is we're gonna be doing the third recitation class since we moved online, right? And I'm gonna solve some problems from chapter 4 that we recently finished. Before doing that, I want to correct some problem. Actually some mistake I made while doing interface conditions. Right, and this mistake has to do with the flux density, normal component of the flux density. So using a polarization argument, I arrived at d2n minus d1n equals rho s. Right, and this is material 1, epsilon 1. Let me draw the diagram. Epsilon 2, I have d2. This is the normal component, d2n, and then d1 with its normal component, d1n, right? And there's the tangent component, right? And then the positive direction for the normal component is designated by n hat. It's in that direction. It's pointing towards inside n1, and then this is the opposite vector, minus n hat. Right? So using a polarization argument, I got this expression. But then if we started with a from Gauss's law, right, we get this expression, d1n minus d2n equals rho s. So there's seemingly a contradiction there. The contradiction goes away if rho s is 0. Rho s is the surface charge density of the boundary of the interface, right? So there's a contradiction there that goes away if rho s is 0, right? If rho s is not 0, I get two contradictory conditions. If I use an argument from polarization, I get this result. If I use an argument for Gauss's law, I get this result. By the way, this is the correct result. Right? Gauss's law gives me the correct result. My argument that depended on polarization gave me an incorrect answer. The argument itself was flawed, and I'll go through that. The reason why it's flawed is not very clear. That's why I missed it, but it is nevertheless flawed. Okay, and I'll try to explain right now why was it flawed. So just to remind you, how did the argument from polarization go? Right? So the idea is that hey, I have two polarization vectors, right? D1 flux density, that's what flux density is. Flux density is a polarization vector. It represents the total polarization in space, right? So D1, right? And we did get a result that at the boundary of any medium, the surface charge density due to polarization equals the polarization vector, which is in this case d dot n. Right? For example, for material 2, right? So for material 2, which is this material, what is the vector that's normal to the boundary of the material 2? It's n hat, right? So this is like d2, and this is surface charge density due to polarization in material 2. Right? In a similar manner, surface charge density due to polarization in material 1 is going to be the polarization vector d1 times the normal coming out from the interface of the material, from the boundary of the material, which is in this case minus n hat. Right? So it's d1 minus n hat. Right? And then the total charge density, surface charge density, is just the sum of those two polarization charge densities. So rho s due to polarization equals, right, and I could remove the p, it's just the total charge due to polarization. It's d2 minus d1 dot n, right? And that's where I got d2n minus d1n equals rho s. Okay. There's a problem with this argument, and the problem is that I'm using right. The problem is that I'm using this. The problem, by the way, is not that the argument is incorrect. The argument is still correct. The problem is that this charge is not a free charge density. This is a charge density due to polarization. This is a bound charge density. Right? When we study interface conditions and we assume a charge density on the surface, we're interested in free charge densities, not bound charge densities. Right? We don't care typically about when we calculate D, we don't care about those charge densities because those charge densities, the bound charge densities, are already embedded in D. Right? So I cannot use them to calculate D or the difference in D because the bound charge density due to polarization is already embedded in D. So remember when we went through this derivation, when we said, hey, the first postulate says divergence of E equals rho, which is the total charge over epsilon naught. Then we said instead of the total charge, we're going to put the free charge plus the bound charge due to polarization, rho p, right? And then we said we can manipulate this to get epsilon naught E minus rho p equals rho f, the free charge, right? And then we said this is equal to minus divergence, the polarization in the material, right? So we end up with epsilon naught E plus, plus p equals rho f, right? So this is D. Okay. D, notice that D is epsilon naught E plus P, and P is related to rho P, the bound charge density due to polarization, right? So the argument is that D has embedded in it, when we take the general flux density D in any material that is equal epsilon, not epsilon naught, epsilon E, D has already embedded in it, it's already programmed in it the effect of bound charges. So the effect of bound charges due to polarization are already programmed into D, are already embedded into D. When we apply Gauss's law, or in its differential or integral form, right, equals epsilon equals rho, divergence equals rho, all the bound charges are already programmed into D. The rho that we need to put in the right hand side should only be free charges. That's the subtle point. So since we started now modeling dielectric materials by polarization, using this analysis, we arrived at the conclusion that, hey, we don't have to worry about bound charges. That we can kind of tie them into D. We can make them part of D, right? So D includes information about the bound charges. The rho in the first postulate is simply just the free charge. Okay. That's why this one is incorrect, because, well, I wouldn't say incorrect, I would say useless, because it's correct in the sense that it gives me the bound charge rho ps, but we don't care about rho ps. We already embedded it in D, right? It is the free charge rho s, which is, I could have written it rho sf, but typically we omit the f, right? It is the free charge that causes the discontinuity in D. So the correct way to get the result was to just take the boundary epsilon 1, epsilon 2, d1, d2, take a Gaussian surface, with one part of it above the boundary, one part of it below the boundary. Again, this is n hat, and this is minus n hat. This is medium 1, medium 2, right? So applying Gauss's law, the surface area here is S. So d1 n, the normal component of d1, right? d1 n S, right? Minus d2. So d2, the normal component is the opposite direction, right? Minus n hat, right? So we get minus d2s ns equals rho s. I'm assuming there's a surface charge density, free surface charge density, rho s equals rho s over yeah, just equals rho s. Okay, s. This is the total charge. This is application of Gauss's law, and I end up with the result that the correct result, that is d1n minus d2n equals rho s. If rho s was 0, if there's no free charge on the boundary, I mean, it wouldn't have mattered. D1 minus d2n equals 0 is the same as d2n minus d1n equals 0. Right? But this is like a very subtle point that I want you to grapple with and think about. Okay. So having cleared that out, I want to start now with the first problem. The first problem is going to be example 4.19. Okay, and what does the example state? The example states, hey, I have a certain interface between two materials, material 1 and material 2. By the way, my axis, the z-axis, is going outside the page, and then this is x, and then this is y. Okay, and then material epsilon 1 is just air, epsilon 0, or vacuum, sorry. Well, air is very close to vacuum. Okay, epsilon 2 is 4 epsilon naught. That means the relative permittivity is 4. Right? We know the field E1 in material 1. There is a certain charge density, surface charge density, rho s equals 5 times 10 minus 10 coulomb per meter square. Right? The question is, what is E2? Right? So that's part A. What is E2? And part B is what is the 2. Okay, so so we want to find E2, right, and E2. E1 is given. E1 is given as 100 x hat plus 300 y hat minus 50 z hat volt per meter. So in this coordinate system, what is n hat? N hat in this coordinate system is clearly moving, is in the opposite of the x-axis, right, direction. It's going to be minus x hat. Okay, right, so this is the normal vector. So the interface, where is the interface? The interface is along the from the coordinate system that we built, is on the YZ axis, right? Okay, because the interface is along the YZ axis, that's where the tangent component of E1 is going to fall. It's going to fall along it's going to fall along the YZ axis. Right? So that tells me that E1 tangent is going to be the component that is on the YZ axis, which is this part. This part of E1 is on the YZ axis, right? This part is normal to the YZ axis. So E1 tangent is going to be 300 y hat minus 50 z hat. volt over meter. So instantly now I know what E2 tangent is, right? Because E1, the tangent component of the electric field intensity is continuous. So E2 tangent is going to be equal to E1 tangent, 300 Y hat minus 50 Z hat, volt per meter. Okay, so what's left now is to find the normal component of E2. What's E2n, by the way? E2n is going to be, no, sorry, E1n. What's the normal component of E? So E1n is going to be E1 dot n hat, right? That's how I find the projection of E1 on the normal vector. What's n hat? We said n hat is minus x hat, right? That's where I assume, typically we assume n hat in this way, and it exists in material 1, points towards material 1. I mean, that's just a matter of choice. Right? So this is E1 dot. Okay, so if I do that, I end up with the x hat sampling out only the x hat component. X hat dot y hat is 0, x hat dot z hat is 0. So I end up with minus 100 volt per meter. Right? The minus sign comes from here. Okay, so that's E1 n, right? So the normal component, sorry, the normal component of normal component of E1. Now, what is E2n? Well, first let's calculate D1n. D1n is just E1n over epsilon, right? Epsilon in this case is epsilon naught, right? So so that's going to be minus 100 over epsilon naught volt per meter. Okay, now I can use this formula for the interface of D at the normal, for the interface of the normal components of D. D1n minus D2n equals rho s. I know what rho s is. Rho s is given here. I will not substitute it in. I'll just leave it as a variable at this point. But now I can right away find D2n. D2n is going to be D1n minus rho s, right? D1n is minus 100 over epsilon naught minus rho s. Okay, so I'm interested in finding E2n. So what's D2n? D2n is E2n times epsilon 2. Epsilon 2 is 4 epsilon naught, right? Equals minus 100 over epsilon oh, did I make a mistake here? Sorry, I made a mistake here, yeah. So D1n is E1n times epsilon naught, not divide. That was my mistake, times epsilon naught. Right, I noticed it because I almost was going to get epsilon squared, which doesn't make sense. Okay, so D1n is epsilon e. Okay, so this was my mistake. So this is minus 100 epsilon naught. Okay, so so for epsilon naught E2n equals minus 100 epsilon naught minus rho s. Right, I end up with E2n equals minus 100 over 4 minus 25, epsilon naught cancels with epsilon naught, minus rho s over 4 epsilon naught. That's S2n. So E2n. So now I have the tangential component of E2t, of yeah, this is E2. Now I have the tangential component of E2, and now I also have the normal component. By the way, the normal component is the component in the n hat direction. N hat is minus x hat. So I could write it as a vector, E2 vector, and I just multiply this by n hat. N hat is minus x hat, so I end up with 25 plus rho s over 4 epsilon naught x hat. So the total E2 is going to be the tangential component plus the normal component. The normal component is 25 plus rho s over 4 epsilon naught x hat. And then the tangential component is 300 minus 50 y and z plus 300 y hat minus 50 z hat. This is E2. And I could plug in rho s and epsilon naught and get a number, but I don't want to. Right? D2 is just going to be E2 times 4 epsilon naught. So D2 is going to be multiplied by 4 epsilon naught, so I get 100 epsilon naught plus rho s x hat plus 300 times 4, which is 300, 300, 600, 4 times 1200 epsilon naught y, right? Minus 50 times 4, 200 epsilon naught z hat. And this is D2. I found the D2 and E2 vectors in material 2. This concludes this, this concludes this problem. Now we want to do a capacitance example. So I want to do example 4.23, which is finding the capacitance of a coaxial cable. What's a coaxial cable? Coaxial cable is some inner conductor, cylindrical shell, and then outer conductor. Right, and it's a cable, right? It just extends. Right, and then the idea is that between this inner conductor, which is at distance A from the center, and this outer conductor, which is at distance B from the center, there's a bunch of different materials, right? So there are 3 layers of materials. So there's an inner layer, a middle layer, and then the final layer. The inner layer is going to be a layer of rubber, and typically rubber has permittivity of 4 epsilon naught. The relative permittivity is 4. And then the middle layer is going to be plastic, which has a permittivity of what? 9 epsilon naught. And then the final layer is going to be a layer of foam, which has a permittivity of 1.5 epsilon naught. Right? So the question is, what is the capacitance per meter of this coaxial cable? What's C capacitance per meter? Right? We cannot talk about total capacitance because we don't know how long the cable is. I mean, if the cable is 100 meters, we'll have a different capacitance than a 1,000-meter cable. But what we can talk about precisely is the capacitance per meter. Okay, and to find that capacitance, we said like the basic method is I mean C equals Q over V. We either need to place some charge in the structure and find what the voltage is due to that charge, then find the ratio and find C, or we could apply a voltage and see what the charge, what kind of charge arises in the structure. In this kind of problem where we have 2 conductors, it's easier to just place the charge. Just assume there is a certain total charge in the conductor. So typically what we assume is that we can assume that in the inner conductor cylinder there's a surface charge density of rho s, right? And then the distance we are interested in is L, right? So I put in the charge, and now the problem is finding what the voltage is between the inner conductor and the output conductor, right? And we know how to do that. First, let's find the let's apply postulate 1, which is Gauss's law. So in those problems, remember that in the postulate, first postulate, we have divergence D equals rho. Notice there's no epsilon here, right? We can calculate D without figuring out where the epsilons are, you know, because if we start with E, yeah, we will need to know what the epsilon is. But calculating D is easier, the flux density is easier because it's not dependent on the material, right? And I'm going to use the integral form of the first postulate, which is Gauss's law, to calculate D, right? So the surface integral over the Gaussian surface. So the Gaussian surface is just going to be some kind of cylinder, you know. So cylinder in the with the surface in the space between the inner and outer conductor, right? And then from symmetry, the field will always going to be radially going out from the center conductor, right? So applying Gauss's law, D dot ds is going to be equal to the total charge. What's the total charge in this case? It's let's say Q total. Okay, so let's find it. So first D is going to be radial, so I forget the vector element, right? I'm just taking the D that's normal to the Gaussian surface times the cylinder of the Gaussian surface. So remember, because the field is radial, those caps here at the right and the left will not contribute anything to Gauss's law, right? So it's going to be D times 2 pi r L, right? That's the Gaussian surface. So I'm assuming that let me actually redraw this clearer. So this is L. Okay, 2 pi r L, that's the surface area of the sides of the cylinder, times D equals the total charge enclosed within the Gaussian surface, which is rho s times the surface, right, which is 2 pi a L. Okay, so 2 pi goes with 2 pi, L goes with L, and I end up with D being yeah, the only thing left is rho s a over r. Right? I can easily bring back the vectorial aspect, right, because of the symmetry of the Gaussian surface. This is in cylindrical coordinates, right? So this is going to be r small hat rho s a over r coulomb per meter squared. Okay, so I found the flux density. Why am I doing this? Because I wanna calculate the voltage. To calculate the voltage, I need first to find the electric field intensity from the flux density, and then I use the electric field intensity to calculate the voltage. I do that, I integrate E dot dl to get the voltage, right? So in this case, E now is going to depend on the material. That's the key thing. I first calculated D, which is not dependent on the material, because it already incorporates the effects of the material are embedded in it, right? And then I separate out E, which depends on the material. So E is going to always be D over epsilon, and epsilon varies depending on where I am, right? So I'll have different electric field intensities depending on which material I'm in. D will be the same regardless of the material in between. Okay. So what is E rubber? It's just going to be D over 4 epsilon naught. So E rubber is going to be R hat rho SA over 4 epsilon naught R. What's E plastic? That's the second one. That's going to be D over plastic is 9 epsilon naught. That's epsilon for plastic. That's going to be R rho SA over 9 epsilon naught R. You see the pattern. And then E foam is going to be D over 1.5 epsilon naught is going to equal R hat rho S A, right? A is still there, over 1.5 epsilon naught R. Okay, so now I have the electric field intensity. I'm set to find the voltage between A and B. That's what I want to do. I want to find out. I know the charge and conductor A, right? So what is the voltage between conductors A and B? Meaning if I go, what's plus minus V AB, right? Meaning if I start from conductor B, right? So that B is where I start, and then I go to conductor A. What would be the voltage between those 2 points? I can apply the voltage law, right? So which is the integral form. So V AB is going to be minus integral from A to B, right? That's what the form is. Sorry, that's not the form. Okay, so I start from B and I go to A. That's what I'm saying, right? So that's what VAB is. I start from B and I end up at A. So the second index in V is where I'm starting, and the first index is where I end, right? So I start from B and go to A of E dot DL. But then as I'm moving from B to A, I'm moving through different materials, right? So I'm going from B to oh, by the way, I did not give you the distances where each of those materials end. So the distances are as follows. Rubber extends, the thickness of the rubber layer is, no, not the thickness, the rubber extends up to 3 millimeters, right? And then the plastic, so this is rubber, sorry, and then plastic extends up to 4 millimeter, and then foam extends, which is B here, up to 6 millimeter. So I go to a 3 millimeter, 4 millimeter, 6 millimeter. Okay, and I start at R equals 2 millimeter. So the radius here is 2 millimeter. So I start at 2 millimeter, and then 3 millimeter. That's rubber. I'm drawing it in one dimension, and then 4 millimeter is between 3 and 4 is plastic, and then between 4 and 6 millimeter is foam. Okay. and I'm going integrating from 6 millimeter to 2 millimeter. Okay, so right, so this is going from 6 millimeter, which is 6 times 10 to the power minus 3, right, to what? The edge of foam and plastic is 4 millimeters, to 4 times 10 to the power minus 3 of the electric field intensity in foam now, which is uh, r hat rho s a over 1.5 epsilon naught r, right? Uh, dot dl, in this case dl is just r hat dr. I'm moving radially. Right? So I can simplify this. I mean, r hat dot r hat is 1, and I can just worry about the magnitude. So this is what I get, rho sa over 1.5 epsilon naught r. Right? And then minus, I go from 4 millimeter to, what did I say? This is plastic now, to 3 millimeter. Right? And this is the plastic field, which is, I'll just put the magnitude, rho sa over 9 epsilon naught r dr, minus from 3 millimeter, or 3 minus 10 to the power minus 3, from 3 minus 10 to the power minus 3 to 2 millimeters. And finally, the field in rubber, which has a magnitude of rho sa over 4 epsilon naught r. Rho sa over 4 epsilon naught r dr. Okay? What's the integral of dr over r? Right? That's ln r plus c. Right? So keep that in mind. The logarithm comes in, shows up in this case when we calculate the voltage. So this is going to be, let me take terms that are constants out. So this is going to be minus rho sa over epsilon naught is common, right? So I can take rho sa over epsilon naught, and then I end up with some integrals that have some constants and integral of 1 over r. So I end up with 1 over 1.5 and then integral of 1 over r dr. That's going to be ln of r, right? So that's going to be ln of r, right? Where r goes from 6 millimeter to 4 millimeter, right? So that's going to be ln of 4 over 6, right? Like ln a minus ln b equals ln a over b. That's a basic property of the logarithm. This is like basic calculus. Okay. So this is ln 4 millimeter over 6 millimeter, which is 4 over 6. Right? Plus 1 over 9 ln, right? I end up with ln, and then ln is evaluated from 4 millimeter to 3 millimeter. So it's going to be ln 3 minus millimeter minus ln 4 millimeter, and that turns into ln 3 over 4, right? Plus 1 over 4. I'm going from 3 to 2, right? So that's going to be ln 2 minus ln 3. That's going to be ln 2 over 3. Okay. So this is going to be VAB. This whole thing is VAB. Okay. What is the capacitance? The capacitance is Q over VAB. What is, do I have total Q here, by the way? So I have V in voltage, but V in voltage is a function of the charge density, right? So that's fine. I can write Q in terms of the charge density. Total Q is going to be, this is volts. Total Q is going to be 2 pi. So I'm assuming a certain length of L, right? So it's going to be 2 pi A L times rho S, right? And then I take L on the other side. So I want to take the capacitance per length, right? That's what I'm trying to calculate. Capacitance per length. Assume L is 1. I can assume L is 1. The length is 1. So if I assume that the length is 1, I'm trying to find the capacitance per unity distance, the unity length. Then the total charge is going to be 2 pi A times rho S, and then L is 1. Okay, over VAB, which is this whole thing. I mean, I don't want to calculate it, but it's going to be, of course, the magnitude, right? Remember, we don't, C is always positive, so it's going to be rho SA over epsilon naught, right, times what's in this, in the brackets here. Okay. So I can cancel A with A. I can move the epsilon naught up there. I can cancel rho S with rho S. I get C equals 2 pi epsilon naught. That's I just did some manipulations. Cancelled rho S, cancelled A, brought the rho epsilon naught up there, right? So this is the capacitance per unit length, right? Divided by this bracket, which is 1 over 1.5 ln 4 over 6 plus 1/9 ln 3 over 4 plus 1/4 ln 2 over 3. Okay, farad per meter. Okay, and this solves this problem of finding the capacitance. Now I want to jump to an example that has to do with energy. Right? So I'm going to go to example 4.27, okay, which is kind of a neat example. It says we have a system where we have 4 point charges arranged in this rectangular pattern. So we brought the charges from infinity and we arranged them in a rectangular pattern. So this distance is A, this distance is B. A is not necessarily equal to B, right? For this example, they gave A equals 1 meter and B equals 2 meter, and then Q equals 20 nanocoulomb, right? So we could plug in those numbers, right? But what's more interesting is figuring out what the energy is in this case, right? So the energy, as we said, we know the formula, right? The energy is half sum k from 1 to 4, not infinity, 4, right? So this is 1, 2, let me match the book, 2, 3, 4. Okay, so it's the bunch of charges Qi times the bunch of voltages at each point due to the other charges. The interesting thing about this problem is that it is symmetrical, right? So the voltage at each point is going to be due to 3 other charges, right? And the distances of the 3 other charges is going to be the same regardless of what point we are in. So V is going to be the same. Vi is going to be the same regardless of what point we are at. What is V? V is due at a certain point is due to 3 charges, right? 3 equal charges, Q, Q, Q. That's the assumption. is Q1 equals Q2 equals Q3 equals Q4 equals Q. Okay, and this is A, this is B, this is A, this is B. What is this distance then? This distance is going to be A squared plus B squared square root, right? So what is the voltage? The voltage is going to be at any point is going to be due to the three other charges, right? So it's going to be a superposition. So it's going to be Q over 4 pi epsilon naught A plus Q over 4 pi epsilon naught B plus Q over 4 pi epsilon naught square root A squared plus B squared. So everywhere, regardless of what I is, the voltage is going to be Q over 4 pi epsilon naught. The result of the superposition is going to be 1 over A plus 1 over B plus 1 over square root A squared plus B squared. So this is a neat kind of arrangement where the voltage will be the same at every point. Okay, so the energy now is going to be, right? So the voltage is the same we're summing over 4 products of Q and V, but the voltage is the same at every point and the charge is the same at every point, right? So this is going to be 4Q times V, right? 4 divided by 2 gives me 2, so I end up with W equals 2QV 2Q squared, so I'm plugging V, 2Q squared over 4 pi epsilon naught, right? 2Q times Q here gives me 2Q squared over 4 pi epsilon naught, and then the rest of V, 1 over A plus 1 over B plus 1 over square root A squared plus B squared, right? And this is oh, I can simplify it further. I can cancel the 2 with the 4 and I end up with 2. This will be the total energy of this configuration. We could plug in the A's and the B's and the Q's, but I don't want to do that, right? This is a nice enough expression as is. All right. Now I'm going to do another energy example, which is an interesting one actually, a very interesting one, which should sound simple enough, right? So it's example 4.30, the energy of a point charge, energy due to a point charge, right? And we want to find the energy due to a point charge using the field approach, the field variable approach. So I have a point charge, Q, right? And then it has a field around it, and then there's an energy in the field, right? And I want to calculate the energy from the field, right? I want to calculate the energy. Let's say I have a distance. Let me draw this in some other color to make it clear. So let me find the energy between two spheres, concentric spheres, sphere A and sphere B. Sphere A is a distance A from the charge, sphere B is a distance B from the charge. All right, and then we know what's the electric field intensity for a point charge is, right? It's going to be R hat Q over 4 pi epsilon naught R squared, right? Volt per meter. Okay, and we know what's the energy density. So this is small w, E. I think they write it this way. So we found that, right? We found it's going to be half epsilon. I'm assuming this is air, E squared. Right? So this is half epsilon. E squared is going to be Q squared over 4, 4 squared is going to be 16, pi squared epsilon squared r to the power 4, right, equals epsilon cancels one of the epsilons. I end up with q squared over 32 pi squared epsilon naught r to the power 4. So this is the energy density. This is joules per meter cubed due to a point charge at any point in space. Notice that it's proportional to r, and at a certain fixed r, the density is fixed, is constant, right? So we want to find the total energy in a region of space. So that tells me that a good volume density, not volume density, volume element that we could choose is the volume element that's like a concentric sphere, like a concentric shell. So I have this shell, and then I have a shell very close to it, infinitesimally close to it, and then this volume in between the two shells is dV. Okay, that makes calculating the integrating over the volume easier. You can just turn the volume integral into a single variable integral, which is just r. Okay, what's the volume, small volume dV here? It's just the surface of the sphere times dr. So this is here dr. Okay, what's the surface of the sphere? Surface of the sphere is 4 pi r squared dr. Okay, so the total energy between points A and B, between radia A and B, right, is going to be, I'm going to integrate from A to B, WE dV. WE, I calculated it to be q squared over 32 pi squared epsilon naught r to the power 4. dV, I said, is 4 pi r to the power squared dr, right? And I'm going from A to B. Let's do some simplifications. This is 32, by the way. Okay. So this is q squared over 8. 4 and 32 cancel out to give me 8. Pi squares give me pi, right? And then epsilon naught, and then r squared, and r to the power 4 gives me r squared. Right, that's it. Okay, so I can take the constants out. 8 q squared over 8 pi epsilon naught. What's the integral of 1 over r squared? Is minus 1 over r, right? Minus 1 over r gives, when I differentiate it, I get 1 over r squared. Right, so this is from A to B. So the total energy between A and B, going from A to B, in between those two shells, the shell at radius A and the shell at radius B, is going to be this. It's going to be q squared over 8 pi epsilon naught 1 over A minus 1 over B. What if B approaches infinity, meaning the total energy from A to infinity, all the energy in the space from shell A to infinity? So that's going to be q squared over 8 pi epsilon naught 1 over A, simple enough, joules. Now the interesting thing is, what if A approaches 0? So meaning, what is the energy in all of space? Right? In this case, if A approaches 0, so B approaches infinity is fine. I mean, it becomes 0. A approaches 0, that means the energy in all of space is approaching infinity as A approaches 0. Okay, so that tells me that for a point charge, the total energy in the field of a point charge is infinite, right? So that's an interesting result, right? Why? Because what does it entail? It entails that creating a point charge, a mathematical point charge, is impossible, right? Because it requires, what this means is that to create from a bunch of charges, charge distributions, to bring them in and create a point charge requires an infinite amount of energy, because there's an infinite energy in the field, right? So that means point charges are nothing more than mathematical objects. They cannot be created in real life, right? Because they require infinite energy to create them, to create pure single point charges. That's one of the early reasons why people started to think, hey, the electron needs to have some radius, some diameter. It cannot be a point charge. And they calculated the diameter of the electron based on this consideration. They tried to estimate what the energy of the electron is, and based on that, how much the electric field should extend, and therefore how much the diameter of the electron is. This turned out to be like somewhat of a good approximation, but the real diameter of the electron cannot be determined from electromagnetism. It needs further, much more deeper theory. Okay. But that's an interesting point. Someone might come and ask me, and hey, we talked about bringing a bunch of charges, point charges, to a certain configuration, and we calculate a finite energy, right? The energy was finite when we did that calculation. Remember, based on half sum Qi Vi, right? I mean, isn't that a contradiction? Well, I mean, this calculation calculates how much energy is required to bring those charges in this configuration. That's true, right? So it is part of the energy. This calculation does not include the energy required to build each individual charge. So this energy is the amount of energy required to build this configuration on top of the infinity. So this is something that's added to the infinity that is required to build each of those point charges. Okay, so that's where that's the retort there. You have to be careful. I mean, with point charges are always problematic in the theory. I mean, it is one of the problems, actually, early problems in electromagnetic theory that are not resolved until we move to quantum theory. Okay, but it's enough within the classical constraint to be aware that point charges require infinite amount of energy. Whatever energy we calculate is the energy that's on top of the infinity that's required to create the point charges. With charge distributions, we don't face this problem because each element in the charge distribution has an infinitesimal charge, has rho v dv, right, prime. So has a charge that's approaching zero. So the energy required to build that zero charge is zero. So in this case, for charge distributions, there is no infinity. The problem of infinity does not arise. Okay. So yeah, with this interesting example, we conclude this recitation, and yeah, we're gonna move on to magnetism. Thank you, guys.